In this video, I'm going to talk about the expectation value of the kinetic energy. This video is part of a playlist on quantum mechanics. You can find the link to this playlist in the description below. In the previous video, we talked about the kinetic energy operator, and we actually did a derivation based upon the momentum operator, and we constructed the kinetic energy operator in quantum mechanics. So I'm going to go ahead and recap that and write a little definition, and we're going to use that in this video. So the kinetic energy operator, which is denoted by T with a little hat on top, that is the same as P with a little hat squared over 2m. And in the previous video, we did a little derivation, and we found that this is equivalent to minus h bar squared on 2m. You can see the 2m is preserved, but the minus h bar squared is not present over here. In fact, it's repackaged inside the momentum. And over here, we have a second order partial derivative with respect to x. So we're differentiating twice with respect to x, and we have this ensemble of constants out the front. So this minus sign came from squaring I, right? I in the denominator was squared, or you could think of it as minus I also being squared. That's also going to give you minus 1. So this over here is the definition of the kinetic energy operator. And we're going to use that, and we're going to put that inside the integral sandwich, and that's going to give us the expectation value of the kinetic energy. So the expectation value of T is going to be equal to the integral from minus infinity to plus infinity of psi star. Now, what are we going to put inside this integral? We're going to have to put all of this stuff inside here. So we're going to have minus h bar squared over 2m. And then we're going to put our second derivative. I'm going to close this, and here, this is what we have. Now, I'm going to rewrite this in a slightly different form that's a little bit more useful to work with. I'm going to go ahead and apply this second derivative onto the psi, and I'm going to pull out this constant. I'm going to pull this constant out the front of the integral. Right? We can actually do that because this is just a constant. The integral doesn't care about the constant. You can actually just move it out. So this is actually equivalent to minus h bar squared over 2m, that's the constant out the front, times this little integral. We're integrating from minus infinity to plus infinity, and we're integrating this combination. And the combination has a second derivative of psi. And here we go. This is it. So I'll rewrite this over here. This is the expectation value of T. I'll put a little box around this because this is very useful. This is a very useful formula. And this actually comes from the momentum operator. So we've actually used the momentum operator to construct this, which is the kinetic energy operator. And then we've sandwiched the kinetic energy operator into this integral sandwich. And we know that the integral sandwich is actually going to give us the expectation of T, which is the expectation value of the kinetic energy. So this expression over here is probably the most useful one, because if you actually have psi, all you have to do is differentiate psi with respect to x twice, and then multiply that by the complex conjugate of psi, and then you're going to integrate that over the domain from minus infinity to plus infinity. And then, final step, you just multiply by this constant out the front, and that's going to give you a value. And that value is the expectation value of the kinetic energy. And this gives you a sense of the average of measurements of the kinetic energy. So this over here is the takeaway message for this video. This is what we actually managed to derive. Make sure you watch the previous videos in this playlist, and keep watching the new videos in this playlist. You can find them all if you click over here.